In this lesson, we will consider the factors which reduce the effectiveness of the transmission of radio waves, the various paths along which radio waves travel from the transmitter to the receiver, called propagation paths, and the different frequency bands and their uses. First of all, let us consider the factors which affect the propagation of radio waves. These factors fall into two categories, namely attenuation, which is the weakening of the wave, and refraction, which is the bending of the wave. Attenuation occurs in several ways. As the wave travels further away from the transmitter, it simply becomes weaker, like the waves in a pond emanating from where a stone is thrown. As range increases, the field strength of the wave decreases. It can be shown that this attenuation is proportional to the inverse square of the range. This means that if the range of the transmitter is to be doubled, the power required must be quadrupled. Surface attenuation occurs when a wave travels over the Earth's surface. Its strength will be attenuated by contact with the Earth's surface, because the wave induces a voltage in the Earth which takes energy away from the wave as it moves away from the transmitter. To reduce this attenuation, vertically polarized electric fields are used, which merely dip into and out of the Earth's surface, whereas a horizontally polarized field is in constant contact with the surface of the Earth, and the wave is completely attenuated within a short distance. The nature of the surface of the Earth over which the wave travels is also a factor in attenuation. Radio waves attenuate more over land than over the sea. Mountains, forests, and deserts cause the greatest attenuation of radio waves. Surface attenuation increases as the frequency of the signal increases, and so frequencies above 2 MHz are of little use for long-distance transmissions. Ionospheric attenuation occurs when radio waves penetrate the ionosphere, which is suffused with free electrons. As radio signals propagate through the layers of the ionosphere, they begin to transfer energy to these electrons, setting them in motion. This results in the electrons vibrating, which can cause them to collide with other molecules, ions and electrons. Each collision dissipates a small amount of radio signal strength as energy is transferred from wave to particle, and the radio wave returning to Earth will have lost some of its strength. The frequency, and hence the wavelength of the radio wave, is important. The longer the wavelength, the greater the ionospheric attenuation. Note that this is the reverse of ground attenuation. Another type of signal weakening is atmospheric attenuation, or scatter. Because the atmosphere contains solid particles, such as water, pollutants, and ice, these will reflect and scatter radio waves of a sufficiently high frequency, those above 5 GHz. You will recall that the wavelength of radio waves in the 2 GHz bands, 3 to 300 GHz, ranges from 10 centimeters down to a millimeter. Water droplets have similar sizes, and that is why they reflect and scatter radio waves. Reflection of signals off buildings and hills, etc., will weaken any signal. Consequently, aerials should be positioned as high as possible, or well clear of buildings and other causes of refraction. Static interference in the atmosphere also attenuates radio signals. It is caused by an imbalance of positive and negative electrical charges in atoms which come into contact with each other, causing electrons to be transferred from one atom to another. Rain and thunderstorms and solar activity are the frequent cause of static interference, and it is worse at lower frequencies. If there is much static interference, the strength of the signal may have to be increased. The strength of the signal compared to the amount of interference, measured in decibels, is known as the signal-to-noise ratio. If internal noise in a receiver can be reduced, then the receiver will be able to process weaker signals, thereby increasing the effective range at which a usable signal can be received. However, this is an expensive business. The other category of factors in radio propagation is refraction, or bending of the waves. This can happen in several ways, and may be a hindrance, or it may be a help to radio wave propagation. If radio waves or light waves pass through one medium and then through another, they will bend or refract because of a change in velocity, such as light through a prism. This graphic shows a straw which has not yet been inserted into clear water. Now, when it is inserted into the water, it appears to bend. This is because the light waves travel in water at 75% of the speed that they do in air. The same occurs to radio waves in the ionosphere, as they pass into a more densely ionized, that is, negatively charged, layer. This ionospheric refraction is very useful, as it causes the radio wave to bend back towards Earth. Refraction decreases as the frequency of the radio signal increases. We will look at this in more detail shortly. Equally useful is atmospheric diffraction. In the low and medium frequency bands, radio waves tend to refract or bend to such an extent that they remain in contact with the Earth's surface, which increases range, possibly to thousands of kilometers. This bending also occurs in the VHF band during some meteorological conditions, which results in a radio wave hugging the Earth and increasing range. This effect is known as super-refraction. The necessary conditions are a decrease in relative humidity with height, temperature falling more slowly than standard, and a high pressure system, typically where warm air flows over cooler surfaces. Sub-refraction occurs in conditions of increased relative humidity, lower than ICAO temperature and low pressure, typically where cold air flows over a hot surface. It results in reduced range. However, not all refraction is beneficial. Coastal refraction occurs because a radio wave travels faster over the sea than it does over land. As a result, any wave that crosses a coastline at other than 90 degrees will bend slightly towards the medium in which it travels slower, namely the landmass. Again, the degree of refraction decreases as the frequency of the radio signal increases. Now let us look at the ways in which radio waves are propagated. There are three ways in which electromagnetic energy travels from a transmitter antenna to a receiver antenna. Two of them, surface waves and space waves do not reach the ionosphere, and collectively they are called non-ionospheric. The third method of propagation, the sky wave, uses the ionosphere. We will look at satellite propagation in its own lesson. Let's start with surface waves. These exist at frequencies from about 20 kHz to about 50 MHz, which is from the upper end of very low frequency through long wave, medium wave and high frequency to the lower end of very high frequency. They travel across the Earth by the process of diffraction. The range achievable is dependent upon several factors. As the radio wave frequency increases, surface attenuation increases. Surface waves are effectively non-existent above high frequency, that is, above 30 MHz. Surface waves are therefore used in the low frequency for NDB transmissions, in the medium frequency for NDBs and long-range communications, and in the high frequency for long-range communications. The second type of non-ionospheric propagation is the space wave, which is made up of two parts, a ground-reflected wave and a direct wave. At frequencies of VHF and above, radio waves start to behave more like visible light, and, in the same way that light has a visible horizon, radio waves also have a horizon. So, the only propagation at these frequencies is line of sight. There is some atmospheric refraction, which causes the radio waves to bend towards the Earth, and this does increase the range slightly beyond the geometric horizon. But, as radio frequency increases, refraction reduces. The range of a space wave can be calculated by this formula. Range in nautical miles is 1.23 times the sum of the square roots of the height in feet of the transmitter above the ground and the height of the receiver in feet. So, suppose the transmitter is at 1600 feet above mean sea level and the aircraft is at 22,500 feet. Their square roots are 40 and 150, respectively. Multiplying by 1.23 gives us the answer 233.7 nautical miles. Let's move on then to ionospheric propagation, and we'll start with a look at what the ionosphere is made of. The Earth's atmosphere is made up of different layers containing progressively fewer atoms of gases with height above the Earth. From a height of about 50 kilometers up to 400 kilometers, the atmosphere is also designated as the ionosphere, because ionization takes place there. It is divided into three layers, D, E, and F. Ionization is the process by which negatively charged electrons are dislodged from the outer shells of an atom by ultraviolet light from the sun, leaving the atom with an imbalance of positive ions. When gas is in this state, it is known as plasma. The extent of the ionization is such as to create bands of negatively charged electrons, and it is these bands, or layers, which refract radio waves. Ultraviolet light waves of different frequencies penetrate the atmosphere to a different extent, creating bands of ionized gases at different levels. Because ionization is dependent upon the sun's energy, it is greater during the day than at night. There are 3 distinct layers in the ionosphere, called D, E, and F. Layer F divides into 2 layers during the day, called F1 and F2, but they recombine at night. Layer D is found at an average height of 75 kilometers in the atmosphere. Ionization is low, because it is the lowest region of the atmosphere to be ionized. It has the limited ability to refract signals of low frequencies, but the waves of most frequencies are attenuated or pass through it. At night, the negative electrons and the positive ions recombine, and the D layer disappears until the next sunrise. The E layer, also known as the Kennelly Heaviside layer, after its discoverers, is found at an average height of 125 kilometers. Normally, the layer can only reflect waves having a frequency lower than about 10 MHz, and it has a negative effect on wavelengths above 10 MHz due to its partial absorption of these waves. At night, the electrons and ions begin to recombine, doing so more quickly at lower levels where the sun's radiation is lost first. Consequently, the E layer is effective at a greater height for a while at night, and is able to refract waves further than during the day. The F layer, also known as the Appleton layer, exists at an average height of 225 kilometers. During the day, the layer divides into 2, known as F1 and F2, because the different frequencies of radiation from the sun ionize the gases to a different extent. At night, there is only one F layer, which is narrower than the combined width of the daytime layers. The ionization in the F layers is quite intense. Consequently, these layers are responsible for most skywave propagation of radio waves, facilitating high-frequency radio communications over long distances. This frequency band is commonly known as shortwave, and lies between 3 and 30 MHz. During the summer, as the sun shines more directly on the Earth, the F2 layer is higher, and so radio waves will be refracted further. When a radio wave is transmitted into an ionized layer and it returns, it is called a sky wave. The refraction or bending of the wave occurs because there is an abrupt change in the velocity of the upper part of the radio wave as it strikes this new medium of plasma. The ionosphere layers are less dense, with electrons at their outer edges, so it is at the center of these bands that the greatest refraction occurs. Radio waves do not always refract and return to Earth somewhere. The angle at which the aerial points is critical. If the wave is transmitted vertically, it may pass straight through the ionosphere and out to space. By increasing the angle from the vertical, an angle is reached called the critical angle when refraction occurs, and this is called the first returning sky wave. But there will be many returning sky waves because radio waves fan out from the transmitter and they will reach the ionosphere at different places, and therefore they will return to Earth in different places. The distance from the transmitter to the point where the first returning wave comes back to Earth is called the skip distance. There is one other term that has to be known, and that is dead space. We have seen that surface waves will only travel out as far as the point where they become so attenuated that they can no longer be detected. The distance from this point to the skip distance is called dead space because no transmission is being received there. We know that the density of free electrons in the ionosphere varies. At a given frequency, as ionization increases, the critical angle for transmission can be less, and this has the effect of reducing the skip distance. And as the surface wave distance remains the same, the dead space will reduce. When ionization decreases, the critical angle will be greater, the skip distance will be greater, and so will be the dead space. By a simple application of the angles of incidence and reflection, we can also see that skip distance increases when the radio wave is refracted from higher up the ionosphere, such as from layer F1 rather than layer D. Another relevant factor in the refraction of radio waves is the frequency of the radio wave. Because the degree of ionization varies with solar activity, the time of day, and the angle of the sun, the ionized layers vary in their ability to refract radio waves. The highest frequency wave that can be refracted for a given range is known as the critical frequency. Any transmission above this critical frequency will not be refracted, as the radio wave has too much energy for the level of electrons in the layer, and it will pass through the layer. As frequency increases, the critical angle will increase, and the skip distance and dead space will also increase. When refraction does occur, the radio wave may reflect back up to the ionosphere in what is called multi-hop propagation, and this can result in transmissions going halfway round the world. The maximum range for sky waves will be achieved when the path of the radio wave is tangential to the surface of the Earth at both the transmitter and the receiver. However, maximum range may not always be the criterion. Perhaps a stronger signal or a closer recipient may be required. As a consequence of all the factors affecting the ionosphere and the characteristics of different frequencies, the choice of radio frequency is important. Let's work up from the lowest frequency. Low and medium frequencies are absorbed by the D layer, so their propagation as sky waves during the day is poor, and surface waves are used instead. At night, the D layer disappears, and low and medium skywave propagation is possible by refraction from the E and F layers. This gives them a greater range than by using surface waves. But nighttime skywave propagation in low and medium wave can interfere with surface wave propagation in the same bands which are used by some navigation equipment, such as NDBs. The high-frequency band, from 3 to 30 MHz, which has a wavelength of between 10 and 100 meters, is the one used for skywave transmission. It is preferable to use the highest frequency possible, because attenuation is less, and this gives the best reception. This is called the maximum usable frequency, or MUF. Finding this frequency is a matter of trial and error, although ionospheric conditions can now be monitored and the MUF can be predicted. It is usually highest at noon, when ionization levels are at their highest. However, because of the inevitable ionospheric fluctuations, a compromise frequency is used, which is called the optimum working frequency. This avoids the possibility of the frequency occasionally being too high and the skip distance being too great. This optimum working frequency is 0.85 times the MUF. Ionization levels are lower at night, and generally the frequency used is half that used during the day. Otherwise, the radio wave would have too much energy and would travel straight through the ionosphere. High-frequency transmissions suffer badly from static interference and are unpleasant to listen to for a long time. So, some equipment is fitted with a selective calling system called cell call. This is a 4-letter code system which enables air traffic control to alert a pilot that ATC wish to speak to him. This avoids the pilot having to monitor his frequency continuously. At the top end of the frequency range, we have very high frequency, VHF, ultra high frequency, UHF, super high frequency, SHF, and extremely high frequency, EHF. Their energy levels are too high to achieve refraction, which limits their range to line of sight. Lastly, in this lesson, let us consider fading, which is the most troublesome problem when receiving radio signals, and it is caused by variations in signal strength because of distance, low transmission power, weather, terrain, and signal to aerial polarization matching. Multipath fading occurs when sky waves contaminate surface waves in the low frequency and medium frequency bands. Multipath fading can be overcome by positioning 2 or more receiving antennae in different places, so that at least one will receive a good signal. This is called space diversity. It can also be overcome by using 2 transmitters and 2 receivers, each pair tuned to different frequencies. This is called frequency diversity, and one of the receivers will usually receive a good signal. Let's recap what we have learned in this lesson. Radio waves are transmitted either as ground waves, which can be surface waves, or space waves, or sky waves. The ionosphere is composed of 3 layers, D, E, and F, which is divided into 2, F1 and F2. These layers refract radio waves back to Earth. At night, layer D disappears, layer E almost disappears, and layers F1 and F2 combine. Different radio bands have different transmission characteristics. Long and medium waves are ground waves, but they can transmit further at night as sky waves. High-frequency waves are sky waves, and they are refracted by the ionosphere. And VHF and higher frequency waves are transmitted by line of sight.